Hello and welcome. In this video, we will be talking about phasors. Specifically, I will discuss where phasors come from and why it is so that if you have a rotating phasor whose real component is the input to the system, then the real component of the resulting output rotating phasor is the output of the system. So essentially, we have an input rotating phasor and an output rotating phasor. And what we are saying is that if the real component of the input rotating phasor is set to the input of the system, then the real part of the output rotating phasor must be the corresponding output to the system. Now, the short answer is that if we take advantage of the linearity of the system, we can do this. But if you want the longer answer, then continue watching and you'll find out soon. Now, here's a brief refresher on phasors. Phasors are just arrows that point in the complex plane, where the x-axis is the real component and the y-axis is the complex component of the complex number. Here we have a phasor, P is equal to AE to the j theta power. And this is because we're using Euler's identity right there. And when we multiply them by e to the j omega t, they spin for increasing t at angular frequency omega. So there are two paths we can take when solving for the output to a sinusoidal input to the system. We can either begin with a phasor input whose real component is our input to the system, or we can begin directly with the real sinusoidal input. Obviously, since this video is about phasors, I'm going to make the claim that the phasor path is the best way to go, the best way to start. Essentially, this is because we already know the form of the steady-state complex sinusoidal input and output. We know that they are both rotating phasors, so we can take advantage of this fact by working with phasors in the frequency domain, where we just solve algebraic equations instead of in the time domain, where we would be solving the more complicated differential equations. But where do phasors come from? Well, I'll show you in the next slides. Here we begin with a general constant coefficient linear ordinary differential equation with inputs f of t and outputs x of t. Now, when we're talking about phasors, we will only be interested in solving ODEs in which the input is a sinusoidal function. So here we have a general sinusoidal function, an, which is the amplitude, times cosine of omega t plus theta n, which is the phase shift, and omega is the angular frequency. And we know that the solution to an ordinary differential equation with a non-zero input is equal to the sum of the homogeneous and particular solutions. We also know that since the input is a sinusoid, the output must also be a sinusoid at the same frequency as the input. So here is a diagram to illustrate what I mean mathematically. So if we have an input an cosine of omega t plus theta n, then we know that the output must be the homogeneous solution plus the particular solution, x of t. Those are its components. So we know that the form of the particular solution must be A out, or the amplitude output, the output amplitude, my bad, times cosine of omega t plus theta out, which is the output phase shift. And you'll notice that omega is the same in both the input and output. And we'll see later that the homogeneous solution at steady state will actually decay to zero. But we'll discuss that in the later slides. So in addition to a sinusoidal input, when talking about phasors, we also restrict our attention to systems whose output has reached steady state. This will be when the homogeneous solution decays to zero, which will occur for very large values of time, or t. So let's take the limits as t approaches infinity. So here's what I mean mathematically. When we take this limit, the homogeneous solution will decay to zero, until all that is remaining is the particular solution that is a sinusoid with a frequency that is the same as the input, and with some values for amplitude and phase shift. So, in summary, this means that for very large t, the homogeneous solution decays to zero. So, our output will converge to the particular solution at steady state. Time for a summary. So, right here, this diagram explains what I have talked about so far. And one thing you may notice is that we are taking the limit as t approaches infinity. We're taking the limit as t approaches infinity in the system instead of doing it for the output. But don't worry about that, because mathematically this is an equivalent operation. I encourage you to take a second-order differential equation with a sinusoidal input and try solving it both ways. You will get the same answer. Now, let's think in terms of linear operators. This will not only make our analysis more concise and compact, but will also reveal why phasors work. We will express our linear system, which is the limit as t approaches infinity of our constant coefficient linear differential equation, as a linear operator, L, that, when applied to our output signal, x of t, is equal to our input signal, f of t, which is, as we have discussed, a sinusoid. If you do not know what a linear operator is, that's okay. I encourage you to look it up on the internet. And don't worry, it's not as complicated as it might sound. Now, let's once again establish the input-output relationship. Except this time, we will do it using our linear operator notation. And so right here I am just demonstrating that with the linear operator we have chosen, we get the same result, the same input-output relationship. So that was much more compact and concise. From now on, we will continue to use this notation. So what happens when we say that our input is the real part of a complex sinusoidal input? Well, we can solve this by breaking down the output into its real and imaginary parts. We can then distribute the linear operator to both the real and imaginary parts. And so, therefore, we can say that if we have a linear operator that operates on the real parts of our output, then we have the real parts of our input. And if we have a linear operator that operates on the imaginary parts of our output, then we get the imaginary parts of our input. And from the differential equation, we can say that our output must therefore be, the real part of our output must therefore be a out cosine of omega t plus theta out, and the imaginary part of our output must therefore be a out sine of omega t plus theta out. And therefore our output to a complex sinusoidal input must be xp complex of t, which is a out cosine of omega t plus theta out, plus j a out sine of omega t plus theta out. So we have two red boxes here. In the top red box, we have the sinusoidal input and sinusoidal output. In the bottom red box, we have the complex sinusoidal input and the corresponding complex sinusoidal output. And so we see that since the real parts of our complex sinusoidal inputs is actually our sinusoidal input that we have in the top box, therefore, for our complex sinusoidal output, the real part is the sinusoidal output in the top box, as you can see with these connections. This means that if we think of our input as the real part of a complex sinusoid, then our output will be the real part of the resulting complex sinusoid. And this is a useful concept because it allows us to work in what is called the frequency domain. instead of the time domain. But where are these phasors, you may ask? Well, the answer is that they're hidden within these complex sinusoids. Let's now reveal them. So if we do a little bit of math, we can actually convert these complex numbers to phasor form, and you'll see that we do this by using Euler's identity. So here are the phasors, P in and P out. And you'll notice that they're both multiplied by e to the j omega t, because they're spinning with increasing t at angular frequency omega in the complex plane. Essentially, the reason why we use phasors is because in the equations, the factor e to the j omega t will always be present on both sides. So they cancel out, leaving the phasors and powers of omega behind. And you'll have a transfer function as a function of omega multiplied by the phasor input to get the phasor output once you rearrange the equation. This effectively converts the differential equations to algebraic equations. And this is because when you're working with differential equations, the e to the power of omega, when you take the derivatives with respect to time, you'll get these omegas that pop out, these powers of omega that pop out of that differential operator. And so you'll be working with algebraic equations instead. So that's pretty cool. And then we solve for the output phasor in terms of angular frequency, omega, and the input phasor, as I was saying, that we will have the transfer function multiplied by the input phasor to get the output phasor. So we then get our complex sinusoidal output to the complex sinusoidal input by multiplying our output phasor by e to the j omega t. And we get the solution to our original real sinusoidal input, which was the real parts of our complex sinusoidal inputs, by taking the real parts of the complex sinusoidal output that we got. Alright, so that is the end of this video, and thank you for watching.